So good morning, my name is Rouck and I'm a brewing engineer, graduated here at the Leuven campus Gent, where it has been already 22 years ago, something like that. And I've been working at first in two smaller breweries. One was a lambic brewery with spontaneous infection, and the other one was a really high-tech brewery developing more than 150 recipes at that time, brewing on demand. And then since 2000 I came here to be the brewmaster of Leuven campus Gent, where I'm in charge of the management of the pilot brewery, where we do education, where we do research, and where we support the brewing industry. So actually here in the lab we have three pilot breweries. We have two smaller ones of 2 hecto and 0.5 hecto, and these are working at the traditional ways. So we have the coarse milling with a lauter-ton combination and traditional conventional boiling. And that is for the comparative trials to compare brews which are brewed on a really innovative way. And that's in our large pilot brewery of 5 hectoliter, where we apply fine milling and a thin bed mash filter. And also there we can do quite traditional brews, although it is with fine milling and then the mash filter. But the whole setup is made to have to create new ideas for the wort production and the final beer production. So in the innovative brewery, we apply the fine milling. And fine milling, we have to start with a lower amount of brewing water compared to the kilos of mash. And that is because of the technological part of the wort filtration. We need to have a thick mash in order to create quite fast filter bed in that filtration technique. Meaning that with a low amount of water, we have lower amounts of kilos to heat up, so we save water, but we also protect the enzymes. When we have the thick mash, we protect the proteases. So we have a very good protein breakdown, meaning that we can start already at higher mashing in temperatures. And we are applying 63, 65 degrees centigrade, depending on the gelatinization temperature of our malts. And we can skip those lower temperatures, 45, 52, because the proteolytic conversion is really good, even at 63, in combination with that thick mash. And then we can do a normal mashing protocol, but we don't have to end at 78 compared to the traditional brewing, but we can go even to 90, 95 degrees Celsius. And what happens at that high temperature is that we first lower the viscosity for fast filtration, but we already will create DMS from the DMS precursor, and we also have protein flocculation already at that temperature. And then we go to the mash filter. And by passing through the mash filter, we still have reaction time because we need to pass that filter anyway. So actually we are using that filtration transfer time, we use that as a reaction time to create further DMS. The protein flocks that we have been producing at the end of mashing off, they are retained in the filter because in that thin bed filter system you can put or you can block those fine particles. And then in the end we have a wort with a very high temperature with high amounts of DMS and quite low amounts of proteins. Meaning that the boiling time or the boiling need for that wort is really low. We can simply strip off the DMS instead of doing the conventional evaporation, which costs huge amounts of energy. We just blow in steam, or now we are dealing with stripping gases such as CO2, nitrogen, and even with compressed air, it's also working. We strip off that volatile DMS while having then a further filling of the boiling kettle. We can apply traditional isomerization, so there is nothing funny, nothing exotic about it, because we need to fill the kettle anyway, and we again have reaction time. So we can do normal isomerization, and then once our boiling kettle is filled, because of the filtration and the sparging, we don't need to do any additional boiling anymore. All reactions are finished, isomerization is done, protein breakdown has been done, and actually it was not that necessary anymore to apply that step. We don't need to evaporate, we just need to strip out the MS, and it's in the evaporation that it's a very high energy cost. If we compare heating up water, we need about 500 kilojoules of energy per kilo water. If you want to evaporate it, you need more than 2000 kilojoules for that. So you need at least four times more energy to evaporate. So if we can skip that evaporation, we save a huge amount of energy, which is very good for the economics, but it's even better for the energy impact of your product. And that comes to the next thing. Heat load is really, really negative in view of beer flavor stability. The higher the heat loads, and it's the whole trajectory, even from malting up to the mashing to the brewing, the boiling, that creates negative reactions because of that high temperature, and that is really negative for the final beer stability. Now, brewers are really traditional, so that means that when a new idea comes up, it needs to maturate before it's actually put in practice. But there is now one brewery in Finland. It's a small brewery, like a small 70 hectoliter brewing capacity, and they are applying this method by very fast brewing because the production time is so short, and they can actually make 4 brews in normal work hours. So they don't need to do a night shift, and they can do 4 different batches on that normal production day. And you could say, okay, buy a bigger brewery, then you do also 1 batch a day. But that's a craft brewery, and they make maybe 100 different types of beer, so they need high flexibility. But high flexibility can now be combined with high productivity and make indeed smaller batches of different worts, but in a very decent amount of time. Beer quality is excellent, and actually their flavor stability of the beer is better than all the beers everywhere in the world. It's for all brewers, it's actually the same. First rule is hygiene. Make sure that everything is okay in the hygiene, especially when you do the downstream. For small craft breweries, I would advise maybe don't invest directly in a super fancy brew house, but invest first in really good cleanable downstream that you can filter or clarify your beer, and you can pack your beer in a proper way that is going on a safe way to the consumer. And then if you can invest in a brewery, take care about the oxygen ingression during the brewing and about the heat impact during brewing. Grain contains an enormous amount of antioxidants. That is a gift from Mother Nature. But if you destroy it already by having a lot of oxygen and a lot of time at a really high temperature, there are no natural preservatives anymore in your final beer. And for us, that seems a little bit stupid these days. So we have it from Mother Nature, why don't we use it? So make sure that no matter what brewing system you choose, take care about oxygen ingression, take care about the heat impacts, and you need heat. We cannot do anything about that, but try to minimize it as much as you can.